Coroutines. A coroutine allows you to spread tasks across several frames. In Unity, a coroutine is a method that can pause execution and return control to Unity, but then continue where it left off on the following frame. And if we go into the software, we go into you go to the software and you can pretty much open whatever project you've been working on it. If you don't have one, just create one, so a new project, and just click in 2D or 3D and then create. So I already did that, and pretty much this is the software right now. And we are gonna go into Windows, and then we are gonna go into, let me see, it was analysis and then profiler. So pretty much this is the profiler that we're going to be using for the coroutines. Okay, so in most situations, when you call a method, it runs to completion and then returns to control to the calling method plus any optional return values. This means that any action that takes place within a method must happen within a single frame update. In situations where you would like to use a method to call a contained procedural animation or a sequence of events over time, you can use a coroutine. However, it's important to remember that coroutines aren't threads. Synchronous operations that run within a coroutine still execute on the main thread. If you want to reduce the amount of CPU time spent on the main thread, it's just as important to avoid blocking operations and coroutines as in any other script code. If you want to use multi-threaded code within Unity, consider the C# job system, and there's the link for it, so you can just go there if you want to learn more. It's best to use coroutines if you need to deal with long asynchronous operations such as waiting for HTTP transfers, asset loads, or files input-output to complete. So here they provide us with a coroutine example. Okay, so we can open Visual Studio Code pretty much and try that example. Okay, but in the meantime, here, coroutine example, consider the task of gradually reducing an object's alpha, the opacity value, until it becomes visible. And okay, so right now we have this projector. Let's see. Okay, so yeah, we can just go along. So pretty much we have this void fade. So this is the function fade. We open curly braces, and then we have this variable here, color. Color C, and C is pretty much we are setting it to the renderer, that material, that color. Okay, so we can go here and let me see, I can just new folder. I'm just gonna, let me see, I'm gonna open a new file. Okay, yeah, I'm gonna open a new file. I'm gonna go here into programming.js, and I'm just gonna new folder. Okay, so new folder, let's just name it C# like this, and pretty much right click, open in terminal, and then pretty much code that. No, it was code space that. So we can now open it in Visual Studio Code, and let me see, just new file, name it, I don't know. Okay, so I need to name it, let's name it fade right now. So we can go here and new file, so like that, fade that. It was CS. Okay, and we can try this example here. So the function name, let's close this one too. So the name is gonna be okay, oops, well, just void fade like that. We open parentheses, and then okay, so you can move to the next line and then open the curly braces. Okay, so we're gonna have the color, and then we're gonna have this variable C, and we're gonna set it to the renderer dot material dot color semicolon at the end. Okay, then we are gonna have in the for loop, we're gonna open parentheses, and here we're gonna have in the curly braces, Okay, so in the parentheses of the for loop, we are gonna have in the, let me see, we're gonna have the float, so it's gonna be the float. We're gonna have the alpha, float alpha, and we're gonna set it to 1f, like that, semicolon. We're gonna have as long as alpha is greater than or equal, okay, of 0, like that. And finally we are gonna have okay, we're gonna have alpha again, but this time it's gonna be the subtraction operator, so 0.1f. so pretty much what this means is that the alpha subtraction operator 0.1f is gonna be equal to alpha minus the, let me see, it'll be like this, so it's gonna be alpha minus 0.1 f, like that. So that's gonna be the result, alpha. Okay, so alpha is gonna be equal to the result of the alpha minus the 0.1 f. So that is the subtraction operator, similar to the addition operator. And now in the parentheses we are gonna have in the this variable c.a, c.a, and we're gonna set it to alpha, like that, without the brackets, like that, semicolon at the end. And now we are gonna have in the renderer that material, so render that material, that color, so it's gonna be that color, and we're gonna set it to C, semicolon at the end. Okay, so we have that. Now in this example, the fade method doesn't have the effect you might expect. To make the fade invisible, you must reduce the alpha of the fade over a sequence of frames to display the intermediate values that the Unity renders. However, this example method executes in its entirety within a single frame update. The intermediate values are never displayed, and the object disappears instantly. To work around the situation, you could add code to the update function that executes the fade on a frame-by-frame basis. However, it can be more convenient to use a coroutine for this kind of task. In C# you declare a coroutine like this. So okay, so let me see, we can pretty much grab something here, but let's just, let me see, we can just comment it, or yeah, let's just leave it like that for now. And we're gonna have the IE numerator like this. The IE numerator is gonna be fade like this. We're gonna open curly braces, and now we're gonna have pretty much this one, so we can just cut it. And okay, you can move the curly braces in this position. Okay, so now we have the color, we have C set to the render that material, that color. Okay, that's fine. Render that material, that color, that's fine. Then we are gonna have the flow, that's fine. And we have alpha renderer, so we can pretty much just cut this whole thing here, paste it here. And now inside of the curly braces we have the C.A set to alpha, then we have the renderer, that material, that color set to Z. And now where we are gonna add is gonna be the GL, so it's gonna be GL, we're gonna GL, okay, GL return null, so it's gonna be GL return null, semicolon at the end. Okay, so this is the way to do it. A coroutine is a method that you declare with an EI numerator return type and with a GL return statement included somewhere in the body. The GL return null line is the point where execution passes and resumes in the following frame. To set a coroutine running, you need to use the start coroutine function. Okay, so we would pretty much also add this function, the update. So we have the void update curly braces. So then we have the if statement. Inside of the if statement, we have the input that get key down. So we could yeah, we have the if statement, we have the input that get key down, and pretty much it'll be f in this case. So now inside of the curly braces of the if statement, then we have start coroutine, and then we pass in the fade. The loop counter in the fade function maintains its correct value over the lifetime of the coroutine, and any variable or parameter is preserved between GL statements. Now, coroutine time delay. By default, Unity resumes a coroutine on the frame after a GL statement. If you want to introduce a time delay, and use the wait for seconds. So again, we have the IE numerator fade, and we have the color. Nothing is changing here. We have the float alpha. Nothing is changing. The only thing that is changing is in the GL return null. So let me see. GL return, well, instead of null, it's gonna be null. GL return null, and then it's gonna be wait. It's gonna be wait for seconds. It's gonna be wait for seconds. Okay, and we're gonna pass in 0.1 f. Okay, or just 0.1 f, and then semicolon at the end, like that. Okay, and yeah, it should be like this. Wait 4 seconds. Okay, so you have, yeah, the first one is uppercase letter. You can now use wait 4 seconds to spread an effect over a period of time, and you can use it as an alternative to including the task in the update method. Unity calls the update method several times per second. So if you don't need a task to be repeated quite so often, you can put it in a coroutine to a regular update, but not every single frame. For example, you might have an alarm in your application that warns the player if an enemy is nearby with the following code. So in this time we're using a boolean. Okay, so yeah, we can just delete this one. Pretty much we have boolean, and this time is gonna be proximity. So we have this boolean proximity check. So we're using camel notation, open parentheses, and then to the next line. So this is the way they use the curly braces. So, well, in Unity you don't do it like this and move here. So the curly braces is to the next line. Okay, and now we're gonna have the for loop. So we have the integer. This I is initialized to 0 as long as I is less than enemies that length. Okay, so we're gonna increment I by 1. Okay, and now inside of the curly braces we are gonna have the if. Okay, so an if statement, we are gonna have the vector. We're gonna have the vector 3 dot distance, like this. Okay, vector 3 dot distance, and now we are gonna pass in the transform that position. Okay, it's gonna be the transform that position. Okay, transform that position. We're gonna pass in the enemies, and open brackets, we're gonna pass in I. Okay, then we are gonna have in the transform that position, is gonna be the transform that position. Okay, as long as it's less than the danger distance. So oops, it has to be like that right here. As long as it's less than the danger distance, I think it was danger distance, it's gonna be danger distance, as long as it's less than the danger distance. And okay, so we're gonna open curly braces. Okay, so we can do it like that, and then we are gonna have in return true, semicolon at the end. And outside of this for loop we are gonna have in the return false, so it's gonna be return false, semicolon at the end. We can save it. Okay, so If there are a lot of enemies, then calling this function every frame might introduce a significant overhead. However, you could use a coroutine to call it every tenth of a second. And again, we will use the I enumerator to check. So we open the for loop, we pass into semicolons, open curly braces, we have the if proximity check. So if this is true, then perform some action, then GL return new, wait 4 seconds, and then that 1F. So this reduces the number of checks that Unity carries out without any noticeable effect on gameplay. Now, stopping coroutines. To stop a coroutine, use stop coroutine and stop all coroutines. A coroutine also stops if you set active to false to disable the game object the coroutine is attached to. Calling destroy example, where example is a monobehavioral instance, immediately triggers a on disable and Unity processes the coroutine, effectively stopping it. Finally, on destroy is invoked at the end of the frame. Note, if you're disable a monobehavioral setting enabled to false, Unity doesn't stop coroutine. So now we're gonna see this one, okay, analyzing coroutines. So pretty much coroutines execute differently from other script code. Most script code in Unity appears within a performance range in a single location beneath a specific callback invocation. However, the CPU code of coroutines always appears in 2 places in a trace. All the initial code in a coroutine from the start of the coroutine method until the first GL statement appears in the trace. Whenever Unity starts a coroutine, the initial code most often appears whenever the start coroutine method is called. Coroutines that Unity callbacks generate, such as start callbacks and return a EI enumerator, first appear within the respective Unity callback. The rest of coroutines code from the first time it resumes until it finishes executing appears within the delay call manager line that's inside the Unity's main loop. This happens because the way the Unity executes coroutines, the C# compiler auto generates an instance of a class that backs coroutines. Unity then uses this object to track the state of the coroutine across multiple invocations of a single method. Because local scope variables within the coroutine must persist across GL calls, Unity hoists the local scope variable into the generated class, which remains allocated on the heap during the coroutine. This object also tracks the internal state of the coroutine. It remembers at which point in the code the coroutine must resume after yielding. Because of this, the memory pressure that happens when a coroutine starts is equal to a fixed overhead allocation plus the size of its local scope variables. The code which starts a coroutine constructs and invokes an object, and then Unity's delay call manager invokes it again whenever the coroutine's GL condition is satisfied. Because coroutines usually start outside of other coroutines, this splits their execution overhead between the GL call and the delay call manager. You can use the Unity profiler to inspect and understand where the Unity execution coroutines in your application. To do this, profile your application with the deprofiling enabled, which profiles every part of your script code and records all function calls. You can then use the CPU usage profile module to investigate the coroutines in your application. And again, the way to do is you just go to you just go to Windows Analysis and Profiler. So again, you just go here, Windows Analysis, and then the Profiler, and then you're gonna have the CPU usage. As you can see, we have the rendering script, physics, animations, garbage collector, global animations, rendering, memory, audio, video. Okay, also you can make this one bigger, smaller. Okay, so you can play around here.